Alrighty, so we're going to continue our look into work and energy by introducing what is probably the most important law of physics we have, which is called the conservation of energy. So before I get into it, let's recap what we know about energy. We know there's two types. There's kinetic energy, which is the energy of motion. When something has some velocity, it's moving, then there's some energy associated with it. The amount of energy is given by the equation. Kinetic energy is 1/2 mv squared. And then the other type is called potential. Potential energy, it's kind of like how much energy is stored in a system because of its location. There's multiple types of potential energy, depending on the system itself. The first type we need to know is the potential energy due to gravity is mgh. So that is something like you hold a marker 6 feet above the ground, then it has some amount of energy associated with it, stored within it, because of the 6 feet above the ground. And the reason you know there's an energy associated with it is because once you let go, that marker starts to move by itself. So there must have been some energy stored waiting to be released so that it could start to move back down towards the ground. It wants to go back down towards the ground. So that's gravitational potential energy. The other type we're going to worry about is spring potential energy, which is if you compress or stretch a spring, then there's some energy stored in the spring waiting to be released. And that's 1/2 kx squared. So just to remember, m is mass, g is 9.8, that's gravity, k is called the spring constant. It's how stiff is the spring you're talking about. And x is how stretched or compressed the spring is, in meters, of course. So those are the types of energy we have. And like I said, there are more types of potential energy out there. It's just that for our purposes, we're just going to worry about these two. Because once you understand it for these two, then you can apply it to the other ones later, if necessary. So, what is conservation of energy? Well, conservation of energy says that energy cannot be created or destroyed, only converted between one type and another. That's the law of conservation of energy. So what it means is, in this universe, there is some total amount of energy. If you add up all the energy, all the stars moving, all the galaxies moving, all the potential energy due to gravity, all the energy everywhere, you add it all up, you get a number, a total amount. And conservation of energy says no matter what you do, no matter how long you wait, that total amount number will never change. We have a certain amount of energy in this universe, and that's all we will ever have. We will never lose any, and we will never gain any. We have the same amount no matter what happens. New stars are created. Well, the energy associated with that must have come from somewhere. And that's what the conversion is about. You could take, for instance, potential energy and convert it into kinetic energy. And that's what I was talking about with the marker. You hold a marker above the ground, let's say. Here's the ground. Here's our little marker. You may be some distance h above the ground. And then you let go. And what happens? Of course, the marker starts to move. Well, notice what just happened. Initially, there's no kinetic energy because the marker's not moving. It's just sitting there. And there is a potential energy, which is mgh. But then, as the marker falls, right before it hits the ground, let's call that the final location, what do we know? Well, right before it hits the ground, it's actually moving. It's got a certain amount of kinetic energy. Well, that's weird. Notice we went from zero kinetic to some amount of kinetic. That seems like it violates conservation of energy. We had no kinetic energy. Now we have some kinetic energy. We've gained energy. But in fact, that's not true, because if you look closer at the system and you look at the potential energy, what's the potential energy when the marker is really, really close to the ground? Now it's 0. Because the height of the marker is now 0 meters. So it's got no potential energy due to gravity anymore. And thus what has happened is the potential energy the marker had to start with was converted into the kinetic energy of the marker. And that's allowable, because what's going to happen when you look at the equation I'm about to write is the total energy of the system didn't change. If you add up the kinetic energy you had plus the potential energy you had at the initial state, you get a number, say 30, whatever it is. Then you look at the final state and you add up how much kinetic is there and how much potential is there. You get 30 there as well. It's just that now, instead of the 30 coming from potential, the 30 is now kinetic. This is the magic of conservation of energy. While it's true, you will never change the amount of energy in your system. What's more true is you can change the type of energy you have. You can convert from potential to kinetic, or one type of potential into another type of potential, all sorts of things like this. And what we're going to do now is take a whole bunch of systems that are very complicated, that would make trying to solve them using the tools we have already very, very difficult to do, and solve them in a very simplistic way using this law. It's a very, very nice thing. And so here is the equation for conservation of energy. Very easy. The total energy initially must be the same as the total energy finally. Now, that's it. It's a very easy equation. You can, instead of calling it initial and final, you could call it phase 1 and phase 2, or step 1 and step 2, or the energy at location A is equal to the energy at location B. They're just names. They're labels for things. Generally speaking, when you see the conservation of energy, you see it as initial and final state. Now, of course, while this is a nice, simplistic looking equation, it means something a little more, and so I'm going to write out what it means in detail. And what it means is the kinetic energy initial plus the total potential energy initial must be equal to the kinetic energy final plus the total potential energy final. That's really what it means. And in fact, remember, potential energy means all potential energies, not just one. Okay, so a system might have 3 or 4 different types of potential energy. When we see potential energy sitting here, we don't just mean one type. We mean all the potential energies that might affect the system, you add them all up and you stick it in as the number potential energy. Okay, some systems there may only be 1. Some systems there may be 2. Just note, when I write potential energy in this equation, I mean add them all up. Now, kinetic energy, you don't worry about it because there's only one type. It's kinetic energy. That's all it is. Now, let's look at an example. What kind of system can we solve using conservation of energy? Well, let's take this. Let's say we have a hill. And there's some box at the top of the hill. Box has a mass of 10 kilograms. And let's say this hill is 20 meters high. It's just sitting there at the top of the hill. All of a sudden it starts to slide down. By the time it reaches the bottom of the hill, the question is, what is its velocity? How fast will it be sliding at the bottom of the hill? That's our question. A block is sitting at the top of a 20-meter high hill. I want to know how fast is it going at the bottom of the hill. Now, try to think, without conservation of energy, try to think about how you would attempt to solve this using what we've done in the past. Newton's laws, kinematics, things like this. Well, let's say we want to do something like kinematics. You know, you want to find a velocity, so maybe we're talking about motion stuff. I know the velocity is going to change, so I need to know something about the acceleration. How can I figure out what acceleration is there? Because I'm not just falling, I'm sliding along the ground. So maybe I want to do an F equals ma type thing, kind of like I did with the inclined plane and the ramp, and figure out, okay, well, how much of gravity goes along this hill. That'll tell me the acceleration of the box. Once I have the acceleration of the block, I could then go to kinematics and solve for the final velocity. But notice, for an inclined plane, I tell you very specifically what is the angle. And the inclined plane is a nice straight surface. With this hill, I don't tell you anything about the hill. All I tell you is how high it is, but I don't tell you what's notice the angle here is different than the angle here. And it's different than the angle here. And different than it is here. So you don't have something like an inclined plane where you could take gravity and do the parallel and perpendicular component. I can't do that with this hill because I don't have any information about it. And even if I did have information about it, it's constantly changing. So I'd have to do this calculation over and over and over and over and over again. So that's very difficult. Obviously, I can't do it. And in fact, that's one of the problems that was run into with mechanics, is you would run across a bunch of problems that were just, if not truly impossible, then very close to being impossible to solve using purely just Newton's laws and kinematics. In order to solve it, you'd have to get so detailed into the precise measurements of this hill that it's just not worth it. However, now we have this new tool. Let's see if this new law helps us. So conservation of energy would say kinetic initial plus potential initial is kinetic final plus potential final. Now let's label what's our initial state. Our initial state is over here. I'm at the top of the hill, sitting there, not moving, ready to slide. What's our final state? I'm at the bottom of the hill. I've slid down. I'm now sliding at the end. Now that I know that, I can start sticking things into this equation. So I say, all right, initial state. I'm now going to ask myself questions. These questions are going to allow me to figure out what I write down for this equation. So, first question. I'm in the initial state. Am I moving yet? I would say no, of course. I'm just at the top of the hill. I have not started sliding. I'm not being pushed. I'm just sitting there. Okay. So that would tell me 1/2 mv squared, that's kinetic energy initial. My v is just 0, so that goes to 0. What else do I ask about the initial state? Okay, I'm looking at potential energy. There's two types that can be there. First of all, gravity. Am I some height above the final position? In this case, yes, I'm 20 meters above the final position. All right, so there's an MGH. All right, third question. Is there a spring associated with the initial position? No, this question has nothing about a spring, so spring potential energy is just 0. And that's it. Initial state done. I've got kinetic and I've got my potential. Now I look at the final state. I ask the same questions. In the final state, am I moving? Yes, I've slid down the hill. I haven't been told that I stop. I haven't run into a brick wall. I haven't been told about friction. So there's no reason for me to assume I'm not moving. I know I slid down, so I was moving. Thus, I assume I'm still moving. So 1/2 mv squared. Call it final. Second question, am I some height above the ground? No. In this case, I'm now at the bottom. I'm at ground level. Thus, the height is just 0, so MGH is 0. Last question. In the final position, is there some spring associated with the system? No. Again, I wasn't told anything about a spring, so that's just 0. So there we go. Done. Let's look at what we have. 1/2 mv squared is 0 initially because I wasn't moving. I've got MGH, and spring was 0. So MGH on the left, and what do we have on the right? I've got 1/2 mv squared, call it v final squared, and then MGH is 0 because I'm at the bottom, and no spring at the bottom. So there's my equation. Now I want to solve it. Notice m, there's an m on both terms, so they cancel. So what do I have? 9.8 times the height of the hill, 20, is equal to 1/2 v squared. I want to solve this for v. So v is square root of 2 times 9.8 times 20, which gives me 19.8 meters per second. And there we go. I've now solved what used to be an impossible problem quite easily. A nice, easy equation, kinetic plus potential initially, must be the same as the kinetic plus the potential finally. I look at my system and I ask myself questions. Questions are easy. All they're doing is telling me what numbers do I stick in for kinetic and potential. Kinetic, am I moving? So in the initial state, am I moving yet? Well, according to the problem, I was sitting there at the top of the hill, then I slid down, and I got to the bottom. So initially, I'm not moving yet. Second question, in the initial state, am I some distance above the ground? Am I at some height? If yes, then I have an MGH. If no, MGH is 0. Third question, in the initial state, is there a spring there being compressed or stretched or something? And of course, this problem has no spring, so that's just 0. And then I go off to the final position and I do the same questions. Am I moving? Well, in the final position, I've slid down the hill, so I'm sliding. So yeah, there's a 1/2 mv squared. Second question, am I some height above the ground? Well, in the final position, I'm at the ground level, so no. Well, MGH is just going to be 0. And then, of course, the spring, no spring in the final position. So once I know what's there, then I can start sticking the numbers in and solve for whatever it is I need. So let's try another example. Let's try this example. Kind of similar. This time I'm going to say there's a hill that looks like this that goes off forever, high and high and high. There's a block at the bottom, and you push this block, giving it an initial velocity of 20 meters per second. The question is, how high will this block reach? How high will the block reach? So there it is. This hill, maybe it's a ramp, maybe it's a rounded hill. I don't know anything about it. All I know is it can just keep going higher and higher. So the hill is taller than I could possibly push this block. So I push it, give it an initial speed. It starts sliding up. It goes as high as it can possibly go. And I want to know, how high is that? Okay. So, conservation of energy. Kinetic initial plus potential initial is kinetic final plus potential final. What are my initial and final states? Initial state, I'm here at the bottom. Final state, I'm at the top. Okay. So, 1/2 mv squared plus mgh plus 1/2 kx squared is 1/2 mv squared final plus mgh final plus 1/2 kx squared final. All right. Start asking our questions. Initial state. I'm here at the bottom. Am I moving yet? In this case, I am. I'm told at the bottom I'm being pushed with initial velocity of 20. Thus, I do have an initial velocity, so 1/2 mv squared stays. Second question, am I some height above the ground? No, I'm at the ground level, thus my height is 0, so there's no MGH. So he's gone. And is there some spring there at the bottom? No, there's no spring, so 0 for him. So initial state is done. Now my final state. What is my final state? Well, I was pushed. I slid as high as I can possibly go up this hill. I'm now there. Let's ask the questions. Am I moving? Well, this is an interesting question. Think about it. It's kind of like the question one asks when talking about maximum height in kinematics. If I've gone as high as I could possibly go, then I cannot be moving. Because if I'm still sliding, then I'm still going higher. So if I've reached the maximum height, if I've gone as high as I can up this hill, then I must have stopped. Thus, my velocity in the final position here must be 0. I must have stopped. Because, of course, if I haven't stopped, I'm still going up. So I'm not at the height yet. Second question, am I some height above the ground? Yes, I've gone up the hill some amount, so there's an MGH. All right, and what about a spring? Is there a spring up there? No, no spring, so he's gone. And so there's my equation. So let's stick the numbers in. Notice there's an m on both terms, so m cancels with m. So I get 1/2 the velocity initial squared, 20 squared, is equal to 9.8 times the maximum height. So height is 1/2 times 20 over 9.8. So get out your calculator. 10 over 9.8 gives me 1.02. I'm sorry. Notice I forgot something. Notice I forgot this is 20 squared. 20 squared. So 20 squared divided by 2 over 9.8 gives me 20.4 meters. So there we go. Again, what is seemingly a very complicated situation, as I have no idea what this hill looks like. Is it a very steep hill? Is it a shallow hill? Is it really rounded, or is it nice and straight? I know nothing about any of that. Notice also, I don't even know how heavy my block is. I'm not told the mass of this block. It might be a heavy stone, or it might be some, light cardboard box. I have no idea. But notice none of that comes into play. All I have to do is worry about the energy. So let's do one more example. I've been skipping things with springs, so let's do one with a spring. A nice easy example with a spring. So here's a brick wall and a floor. And there's a spring attached to the wall, which is attached to a block. Okay, let the block have a mass of 10 kilograms. Let's say the spring constant of this block is 200 newtons per meter. What happens? Well, first, let's say we compress this spring by 1 meter. So, we push the block to the left, compressing the spring. We compress it by 1 meter, and we're holding it there. Then we let go, and the spring's allowed to slide to the right. It gets pushed by the spring, it slides to the right. I want to know how fast will the block slide. Okay, so fairly easy system to understand. It's kind of like, you loaded a gun, you compress the spring. Here, it's just a block. You compress the block into the spring, squishing the spring by 1 meter, and you're holding it there. It wants to be released. Then you release it. The spring shoots the block off to the right. I want to know how fast will it be moving. So, conservation of energy. Kinetic initial plus potential initial is kinetic final plus potential final. What are our states? The initial state, the block is compressed. Final state, it's been released. Ask our questions. Initial state, I've been compressed by 1 meter to the left and I'm being held there. In that state, am I moving yet? No, I'm not moving. I'm just sitting there being held with the spring compressed, ready to be released. So, 1/2 mv squared is 0. All right, MGH, am I some height above the ground here? No, I'm sitting on the floor, no height above the ground, so he's just 0. Third question, spring. Am I compressing or stretching a spring in the initial state? Yes, I am. I'm compressing it by 1 meter, in fact, but all I need to know is there is a spring here, so 1/2 kx squared. All right, so that's the initial state. Final state. What is the final state? I've now released my spring. The spring pushes the block to the right, and the block is now moving to the right. In that state, am I moving? Of course, I just said the block's now moving to the right, so 1/2 mv squared. All right, second question, am I some height above the ground? No, I'm still on the floor. I haven't been pushed upwards or anything like that, so MGH is still 0. Third question, am I compressing or stretching a spring in the final state? No, I'm not. I've already let go of the spring. The spring has been released, so 1/2 kx squared is just 0. He's not still compressed. So there we go. There's my equation. 1/2 kx squared initially is converted into the kinetic energy finally. So now all I have to do is plug my numbers in. Here, notice there's a 1/2 on both terms, so that'll cancel, but I cannot cancel the m. Notice I can't cancel the m this time because there's an m only on one of the two terms. 1/2 kx squared doesn't have m on it, so I can't cancel the m. But k is 200. X, I've been compressed 1 meter. M, the mass of the block was 10, and I'm looking for the velocity. So solving for v is square root of 200 times 1 squared over 10. So, get out your calculator, plug it all in, and I get 4.47 meters per second. So there you go. Here we have a system that has a spring in it, but you see we do exactly the same as we did for the other examples. We figure out what's the initial state, what's the final state, and then we ask the questions. Are you moving in this state? If so, 1/2 mv squared. If not, 0. Are you some height above the ground? If so, MGH. If not, 0. And lastly, is there a spring being compressed or stretched in this location? If so, 1/2 kx squared. If not, 0. You do it for the initial state, you do it for the final state. And then you're left with one equation sitting there. There's going to be some unknown somewhere. Plug all the numbers you have, solve for your unknown. It's a basic algebraic equation. And there you go. So I hope you can see that for an equation that's fairly simplistic, we can solve some very complicated systems. Things that would have been impossible to do using Newton's laws and kinematics and things like that. So, I hope this has been informative. Of course, look for a video with some more examples worked out, but you're going to find that no matter what the example is, pretty much you're going to be solving it the same way. So get used to this technique. It's the way I solve them, and I found that most students get the hang of it when they're asking these questions to figure out which terms are necessary in the equation. So practice them, and you'll see, like I said, some more examples next time, and I'll do some more examples of even more complicated situations that have both gravity and springs in them, situations where you're going between 2 or 3 different heights on a hill. So ways to try to make it more complicated, but you're going to find, no matter how complicated the system, asking these questions to fill in the terms will make it very easy. So, until next time.